Hey y'all, it's Mrs. Blasky. Today we're going to introduce topic 5, which talks about kinetics. So kinetics is all about how fast reactions are going and what we as the outside scientists can do to affect that rate of the reaction. So we're going to be talking a lot about rates of reaction, which talks about how fast that reaction is going. So there's lots of different things that can control how fast a reaction goes. You can almost think about it like the speed of the reaction. So its unit are in moles per time. So moles per second, moles per minute. Sometimes we're also going to talk about that in terms of molarity per time. So we need a balanced chemical equation to know what's happening in a reaction, but that balanced equation tells us nothing about how fast that reaction can go. The only information that can tell us about the rate of the reaction is actual experimental data, where we say, hey, I mixed this molarity reactant and I saw that the reaction took this long to happen. And then I changed the concentration of the reactant and it took this long to happen. And then I changed the temperature and it took this long to happen. So we will be talking about how those different modifications can affect our rate. We also know that rate can slow down as the reaction goes on. As there are fewer and fewer reactants around, it takes longer and longer for those reactions to happen. So several things that can affect our reaction rate, our concentration. By changing the concentration of the reactants, we can change the rate of the reaction. By changing the temperature, usually we can get a change in the rate, not always, but usually. By changing the surface area of the reaction, either by grinding up our reactants into smaller and smaller bits so that they have larger surface area, or by providing it a different surface for that reaction to occur. That can change the rate of the reaction. And then we also are going to talk about catalysts. And so by adding a catalyst, usually we can make the rate increase. So for example, this is the way that we're going to see data many times for these kinetics experiments. If we've got the balanced equation, A plus 2B makes C plus D. We have different sets of information about the reactants. We're only going to see stuff about the reactants. Products do not influence how fast the reaction goes because we're only looking at how those reactants are forming products. So what this tells us is that in one experiment, we put 0.1 molar A and 0.1 molar B. Remember, we know it's molarity or concentration because we've got those square brackets. And we had an initial rate of 1.36 times 10 to the negative 6 molar per second changing for that reaction. Then for experiment 2, we doubled the concentration of A, but kept the concentration of B the same. And we see that that changed our rate. Again, doubling A, but keeping B the same. Again, we had a change in rate. Now we go back to the initial concentration of A, but we've doubled B, and we see how that affects our rate also. So there's lots of different ways we can change this around. So we can think about how the forward rates of the reaction can affect the rates for our products as well. So if we have a combustion of ethylene here in example number 1, C2H4 plus 3 oxygens makes 2 carbon dioxides and 2 waters. If the concentration of C2H4 is decreasing at 0.036 molar per second, what are the rates of change in the concentrations of CO2 and water? So even though carbon dioxide and water are our products, we can still see the effect on them based on our reactants. And so if my ethylene, my C2H4, is decreasing at a rate of 0.036 molar per second, that means my products are going to be increasing. And they're going to be affected based on their coefficients, based on those molar coefficients. So carbon dioxide is twice the moles of C2H4 based on its coefficient. So its rate is also going to be twice. So it would be 0.072 molar per second increasing. Water has the same coefficient as CO2, and so it would also be increasing its rate at the same rate. as that carbon dioxide. So it would also be increasing at 0.072 molar per second. When we start seeing relationships between how much reactant is there and what the reaction rate is, then we call that relationship the reaction order. So there are lots of different reaction orders. Honestly, it can be any number, not just integers, but in AP Chemistry, we are only going to deal with 0 order, 1st order, and 2nd order relationships. So when we have a direct proportionality between the concentration changes and the reaction rate changes, we call that a 1st order relationship. So when I double the concentration of a reactant and the rate also doubles, that means that that reaction is 1st order with respect to that particular reactant. If changing the concentration has 0 effect on the reaction rate, then we call that a 0 order reaction. So if I quadruple my concentration and it doesn't change the reaction at all, that is a 0 order relationship. A 2nd order relationship is an exponential relationship. So if I double my concentration, but my rate changes by a factor of 4, then that is going to be a 2nd order relationship. When we write this out, we can write out something called a rate law. And so a rate law is written always in this format, where rate is at the beginning. Oftentimes we just write the word rate to show this relationship, but that's that molarity per second or molarity per minute number. K is our rate constant. We'll talk about that in just a minute. And then we have the concentrations of any and all of our reactants raised to the power of the order of that reactant. So if A was 1st order, this would be A to the 1st. If it was 2nd order, it'd be A squared. If it was 0 order, we would write A to the 0, or we could even just drop that out of our expression because anything raised to the 0 power is 1. This rate constant remains the same for a reaction as long as the temperature is kept constant. These value of K for the rate constant will also always be the same for a reaction as long as the temperature is the same. If we need to find the overall order of the reaction, we would add together the individual exponents. This is where we can get above 2nd order. So for example, if I have the rate law, rate equals, there should be a K here. K. A is 1st order, B is 2nd order. And yes, it's as easy as just looking at those exponents. We say the reaction is 1st order with respect to A, 2nd order with respect to B, and 3rd order overall, because 1 plus 2 gives me 3. Now, to find the order of a reaction, we need to look at the data given to us. So this has to be experimental data. We cannot get this from a balanced equation. So there's a couple different ways to do this. One way is mathematically. I pick 2 experiments and I compare how the concentrations changed to how the rate changed to see what happened. So if I look at experiments 1 and 2, if I make a ratio of those, of their rate laws, the rate of experiment 2 over the rate of experiment 1, they're both 1 times 10 to the negative 3 molarity per second. So the ratio of those rates is 1. I can also set up a ratio of their rate laws. So A to the M, B to the N. I use the data from experiment 2 and the data from experiment 1. Now, if I look at this, K's are going to cancel each other out on top and bottom of this ratio because they're the same. Also, this 0.2 to the M is going to cancel out because that's the same on both the top and bottom. So I can look at what's left over. So I've got 0.4 to the N over 0.2 to the N equals 1. The only way to get that to equal 1 means that that coefficient of N has to be 0. So that means that B is 0 order for this reaction. Another way to look at this, if we look back up at our data, If A is a constant number, B doubled, and my rate did not change, because I can see that that change in B did not cause a change in the rate, I know that B is going to be 0 order. So you can either go through the process of doing the math to see that relationship, or sometimes we can just see that relationship by looking at how things are changing or not changing. In order to make that comparison, we have to have all of our other reactants have concentrations that are not changing. And we don't always have that in the data. And so we need to be able to do that math if we need to. So now to find the order with respect to A, I picked 2 different experiments. In this case, I picked experiments 3 and 1. So if I take the ratio of their rate laws, again, K is going to drop out. My 0.2 over 0.2, the n can all drop out either because they're both the same or because I know that n is 1 or that n is 0. And so the term is going to drop out to be 1. I can see that I got 0.4 to the m over 0.2 to the m is 2. So 0.4 divided by 0.2 gives me 2. 2 raised to the m power has to equal 4. So m has to be 2 in order to make that math work. This means that the reaction is second order with respect to A. Again, we could look at the experiments and just look at some comparisons. If I look at experiments 1 and 3, the concentration of B is constant, concentration of A doubled, and my rate went up by a factor of 4. So if that is always true, if my concentration goes by a certain factor and my rate goes up by the square of that factor, then I know that I have second order. So again, if this was a problem on a test or a quiz, you could write this out either way. You could either show out your math to find those exponents, or we could say out in words explaining how we can see those relationships. We could say in experiments 1 and 2, as A is held constant and B doubles, the rate does not change. This means the reaction is 0 order with respect to B. In experiments 1 and 3, when B is held constant and A is doubled, the reaction rate is quadrupled. This means the reaction is second order with respect to A. Right? So we can't always do this comparison method. Sometimes the data doesn't allow us to do that. So you need to be able to fall back on that mathematical relationship also. So from that, we can write out our rate law. We always have to write rate equals that rate constant K, concentration of A raised to its power. It was second order, so it's raised to the power of 2. B was 0 order, so we raise it to the power of 0. Or because that B term would drop out, we could not write it and just write rate equals K times the concentration of A squared. Being able to do this math is very important. We might see more than 2 reactants, and so there's lots of times we're going to have to work through this. There are tons of practice problems in here that you can work on with this. So this is what we're going to be working on in class. Make sure that you can get comfortable with this, and I will talk to you later. Bye, y'all.